So this is the example that I'd like to go through. Although it is a sort of a circuit example, but it will show the point. Okay, so here we have a linear circuit. I'm having a variable voltage, so I am changing the voltage and measuring the current and the voltage at the same time. And here is the voltage, and here is my current. So clearly, you can say that this is my I'm changing now the voltage. So this is my independent variable, and this is the current that is as a response is changing is my dependent variable. Okay, so this is the independent variable, and this is my dependent variable. Okay, first I'd like to find the constant K1 and K2 that satisfy this equation, which is I equal to K1 plus K2 times V, because as you know, as you can see here, this is a linear line. So I'd like to find that line. So to find the line, we need to have two constants, K1 and K2. Then I will use this line to predict the current when the voltage is 2.5. The maximum volt here is around 2 volt. I want to see if I increase the voltage to 2.5, what will be the current? And this is, as I mentioned in the previous class, this is the simplest machine learning algorithm you can have. So you build your model based on the data, and then you can use the model to do any sort of prediction, which is basically what machine learning is all about. Then we will evaluate the accuracy of the model using R square and R. Okay, so let's move on. So this is my data, this is my V, and this is my I. This is from the question. Then I need to calculate V square and VI. So I just square this column. Now this is my X actually in the formula, and this is my Y, and this is the formula I'm referring to. So this is the original formula to find my A1. Okay, so this formula requires the summation of X times I. So this is why I multiply V times I, which is here X and Y. So I need to multiply V and I, and then I need to sum all of them. So this will give me this term. Then I multiply by N. N simply is 1, 2, 3, 4, 5, 6. Go from 1 to 5. Sorry, 1, 2, 3, 4, 5. There are five values. So N here is equal to 5. Then minus summation of X of I. So this is X of I, which is the voltage. So this is the summation of X of I times summation of Y of I, which is this one, divided by another N, which is also we know as 5. And then summation of X of I squared, which is the V squared. So this is why we need to find V squared, which is the dependent variable squared, as per the formula, and then minus summation of X of I, which is this one. So it's basically, as far as you know how to plug in the different parameters in the formula, you are okay. Okay. So now I need to find, if you go back here, I need to find, first we find K2, okay, and then we'll find K1. This is how we do it. So A1 here is my K2. Now I want to write the formula in terms of V and I. So basically I will take out X and have it as V, take out YI and have it as an I. So this will be the formula. Okay, I have a question here. It says here, if you set X to be the current and Y to be the voltage, then you have to switch them. No, the results will not be the same. Now you will have a different formula now because you are controlling the current and measuring the voltage. So you have to have a current source. So this is from the circuit. Now in the formula, the difference here, so you will have here I and V. So your X will be I, your V will be Y. So this has to be I squared. So it will not be the same formula. And as we will plot it, you will see that you will have a different slope. You will not have the same slope. Okay. So this is my formula now. In this regarding this, so this is my my formula. Okay, let me just sorry. choose the pen back. Okay, so now I need to substitute. As I said, n, this will be 5. Summation of v times I, so this will be the summation. This will be 1.589 minus. Then this will be the summation of v, which is 6.281 times summation of I, which is 1.192 divided by n, again is 5. Summation of v square, which is 8.841. And finally, summation of v all square. So it will be minus 6.281 all square. So this will be here, and this will be my K2. So this is my milliamps per volt. Okay, because it's a slope, so it's a difference of the y by the difference in x. Y was a current, x was voltage. Now to find the average value, I need to find the average value to calculate K. Remember, when we calculate K1 is nothing but I average minus K2 and V average. This is what is K1. Okay, so I need to find the I average and the V average. Okay, so basically how to find the I average? The I average is nothing but the summation of I from I goes to 1 to 5 divided by n, which is in this case is equal to 5. So we have the summations 1.192 from the table divided by n, which is equal to 5. So this is equal to 0.238. And then I will find the V average, which is again the summation of the voltage. I goes from 1 to 5 VI divided by n. Again, I will get the value from the table, and this is 6.281 divided by 5, and this is equal to 1.256. So now everything is set to find K1. My K1 will be equal from here. It is 0.238 and minus K2 from the previous calculation, 0.0963 times the average of the voltage, which is 1.256, and this gives me the value of 0.117. This is the value of this. So now my current I, the formula will be the constant, which is 0.117 plus, this is your K1, then we will find K2, which is 0.0963 times V. So this is my linear curve for the I or VI relationship. Now, if I want to find I at 2.5, at any value actually, I will just substitute V with 2.5, and if I do that, this becomes equal to 0.3577 amps. So this is the prediction of the current at a voltage that I don't actually have. Okay? Okay, excellent. Now, I need to quantify the accuracy of my model. Okay, so how good is my model? How bad or how good? And as I said before, this will be the criteria we will use later on, because later on we will use nonlinear models. If it's a linear model, we know it has to be a linear line. There is no multiple models to choose. However, starting from next week, we will work with nonlinear models. So when we work with nonlinear models, there are multiple choices. So which one is the best? We need to find R square, which is, we define the R square as the ST minus the SR divided by SR, where ST and SR are defined as such. So let's see how we calculate this practically. So again here, what you will have, this is your I. I is our dependent variable. This is what we are trying to predict. We don't care about the voltage when we calculate this. So this is what we want to do, or this is what we want to see our value with it. So we will have I. This is from where? From the measurement. This is the input. Sorry, this is from the measurement. This is what we measure actually. Then we will have I estimate. This is from the formula that we just developed, the formula that I just developed in the previous, which is the 0.117 plus 0.0963V. Okay, so this is from the formula. So this, if you can say, this is the actual, and these are the estimate. Okay, this is what you need. That I need to calculate S of t. Now, what is S of t? S of t is now we have here I average. That this is the average of the current. Okay, so what is S of t? You take every value, actual value of the current, and you subtract that. So you take this value, subtract it from the average value, take the square. Okay, so this basically, this number is 0.188 minus the average 0.2384 all square. So you have it here. You go to the second value, 0.209 minus the average value, take the square, and so on and so forth. And then you take the summation of all of S of t, and this is S of t. So this is the summation of the difference between the measure value and the average value. Now, S of R is the difference between, again, the measure value and the estimated value. So it is, so this number is nothing but 0.188 minus 0.1842 all square. So you get this number. So this minus this all square, you get this one. Take the summation. This summation is your S of R. Okay. Now, once you are done, you found S of t, you find S of R, you will find your R square, as I mentioned, which is equal to this. So this is your R square. So if you do the calculations, you will find that this is your R square and this is your R. We use more R square as a sign of how bad or how good. As we mentioned in the previous class, as you are closer to 1, you are getting better and better results. And this 1, what does this mean? If this is 1, it means that your S of R is equal to 0. What does mean that S of R is equal to 0? Means the summation of all of the residual or the error, which is the difference between the measure and the estimate, is equal to 0. There is some error. I mean, that's not practical. We don't see this. There is always an error, but we try to minimize the error, and this is the whole idea. Now, I try to solve the same problem in Excel, okay, and this is what I get. So this is your I, and this is your V. So we get almost exactly the same, and this is your R square. This is what Excel gives to you. So basically now you know how the Excel linear function is working, how you can find, how you can estimate this curve, how you can program it yourself. You don't need now to use Excel anymore, because you can do it yourself. And actually in the simulation, you will be building your equation estimate or curve estimate, not just linear and non-linear, and you will have something very close to the. Any questions here? No. Okay, good. Now let's go for a special case. What do you mean by a special case? Assume that again we have a model, linear model, but this model now does not cross the y-axis, but actually go through the 0. So the equation here is y equal to a1 times x. It's not a1x plus a0. Okay. The question that we might ask ourselves, okay, this looks very straightforward. We have a formula for a1 and a0. Just assume a0 equal to 0, and pause for 10 seconds. Let me see your answers. What do you think? Can we use this formula or not? And why? What do you think? Can I use this formula or not? But not, you don't tell me yes or no, but tell me why if I can use it or why if I cannot use it. This one question says no, because without A0, it's not accurate enough. Okay, the answer is correct. There's no, but the explanation is not very clear. Why I cannot use this formula? A0 is 0 now. So what do you mean by it's not accurate enough? If you can elaborate more, or anyone else, or someone disagree. So why I cannot use this formula directly? The offset A0 help adjust the curve. Not exactly. The reason why I cannot use this formula, because when we derived this formula, when we derived it when we have two equations. Remember, we solved two simultaneous equations. So this one, let me just go back here and remind you how we come here. Let me go back here. How we derive this formula, we take the partial derivative of two equations and we equate them to 0. So I end up having two formulas. I have this formula and this formula, and those two formulas, they have A0 and A1, and then we solved these two formulas together, and then we come up with this. So there is an A0 there embedded, so I cannot just simply ignore this. However, how we will solve this? We will actually derive it from scratch, same way we did for this formula. So we cannot do this. So let's go for it. So now this is my residual. This is what I'm trying to minimize. Okay? Okay, so this is my actual and this is my model. There is no A0. So the summation of the residuals SR is summation. So this is the function that I want to minimize. So I will take the partial derivative of S of R with respect to A1. This is what we did last time. So this is basically equal to summation of yi minus A1 x of I times minus x of I, and I equal this to 0. Equate this to 0. Okay, so this will be out. So I will have here summation of, and the minus sign can also be taken out. Okay, so summation of yi xi minus summation of a x of I square equal to 0. I will take this to the other side. So here summation of yi x of I equal to, I can take out a out because it's a constant, a summation of x of I square. So from this, your a is equal nothing but this yi x of I divided by x of I square. So this will be my formula. Okay. Now, when we work with minima or maxima, I mean, when we take the partial derivative and equate it to 0, this could be a minimum point or this could be a maximum point. Okay, we want to minimize the error, so we want to make sure that this is a minimum point. And how we do that? We take the second partial derivative. So if I take the second partial derivative with SR with respect to A1 square, so if I take the second partial derivative with respect, so this will goes to 0 because there is no A1, and this will equal to the partial derivative. So this will becomes with respect to 2xi square. Just A1 becomes will become, and this equal to 0. And very clear that for any values of here, this is always more than 0, always. Okay, so if the xi, if the number of x of I is 1, is positive or negative, so this will be always greater than 0 because it's xi square. And then if the second partial derivative is greater than 0, it means that this is actually a minimum, and this is what we want. Make sure that this is a minimum. I mean, this is the minimum error that we will get. Okay, so we'll end my class here with an example, and so the formula become here very straightforward. Now imagine that I'm measuring the voltage now here I have a current source. Back to your point. So here my dependent variable, my independent variable is the current. My independent variable is the voltage. I reverse it now. Okay, and so I'm changing the current and measuring the voltage. So this is my X, and this is my Y. Okay, so and I want to find what is the best fit of this line. Okay, so this is direct application of the formula, and my formula is straightforward, that the voltage V is equal to a constant K times I. Okay, and K is V over I, which is the resistance. This is what we want to calculate. This is the resistance R that we want to find, which is K in this case. Okay, so here I will have, this is my X and this is my Y. So here we switch them. Try to have the V instead of the I. Then you will not get an R. Actually, you will get the conductance G. Okay, you will get 1 over R. So it's a different. If you switch, this is back to the question that we always asked. What if I switch them? If you switch them, you will get a different curve, which is basically 1 over R, which is the G, the conductance in this case. Okay. Okay. So this is your X squared, and this is your X times Y. And here is my formula for A1. That is the formula that we just derived. It is X of I, Y of I, divided by summation of X of I squared. Okay, so this is your X of I squared. This is the summation. So this is the number that I'm looking for. So this is your X of I squared summation, 0.0000932. And then the summation of X times I, which is equal to this, which is 0.9465. So if you do the summation, you will find that this is your R. Now, since this is in amp and this is in volt, so this will be in ohm. So this is your equation. V is equal to this. Okay. So now we dealt with the linear scenario, and in the linear scenario, you will get a straight line, either go through the origin or not going through the origin. In the practice problems that you will see tomorrow, you will have 2 questions. I already posted them. One example, that line doesn't go through the origin. The other one, that line goes through the origin. As I said, this is a very straightforward, very straightforward. You just need to know how to use the formula. You need to construct this. In any question, you have to construct the table. If it is only a line that goes through the origin, this is the table format. And if it is that does not go through the origin, then we have the other table format. Just here, I did the same thing. I tried to do my Excel. So this is 1015. Here it is 1016. So it's close enough. There is 0. Here is minus 0.021. Remember, this is 1,000 and this is a fraction. So it does not really go through the 0. This is little bit of deviation, which is okay, instead of 0. Okay. Let me see before. In a quiz, could we use Excel to create the table instead of calculating the sum manually? Okay, now in the quiz, you have to show me the table, that you constructed the table. Now, how did you do the calculations? It's up to you. Okay, so I have to see something like this. I have to see this table. Okay. Now, how did you calculate these numbers? It's up to you, but you have to show it. Of course, you will not copy from Excel, so you need to copy. You have to calculate these values. I cannot. The reason why I'm saying you can use anything because there is no way for me to verify this. Okay. So basically, but I need to see this is in handwritten. Okay, a table, and then you do. So how you do the calculation? It's your business. I will not really dictate this because I cannot. I mean, anything I cannot monitor, I will not dictate. It's up to you. Okay, so I will not tell you how to do the calculations. Okay. In the last few minutes, just I want to give an introduction of linear regression, just a very small introduction and what it's all about, and then we leave it to after the quiz starting from Tuesday. So mainly, I mean, most of the data that we deal with, many of it, not most, many of it is nonlinear in nature. Okay, so if I have something like this, this is the data. This is my dependent variable and independent variable, and this is how it looks like. If I try to fit a straight line, it will be really very bad. You see here the error, how much the error will be. I mean, there is no way you can minimize such an error. Okay, so the best thing is to have a curve like this that goes through. So this is definitely, this is not a linear function. I cannot get to this function with basically y equal to mx plus b. This has to be like an x squared exponential of x. It should be a nonlinear function. So there is no way that we can do this using a linear function. However, the least square method can be expanded or extended to fit the data of different nonlinear models. So exactly the same thing. We want to minimize the square of the error. So let's just have a stick and see these are some of the examples we'll be working with. Okay, so we'll have the exponential function. We will have the power model, y equal to ax to the power of b. We have the saturation model, y equal to ax divided by bx. So always here we have a b and we have x. Remember in the linear model, a equal to ax plus b. This is the linear model. Okay. Now all these nonlinear models, they will have two variables. They will have the a and they will have the b. But where is the a and the b? Is the difference here. Except for the polynomial, here we have multiple. We have a0, a1, a2, a3. So we have too many variables depending on what is the degree in the polynomial. Is it one to first degree polynomial? It is like a linear model. Second degree, you will have plus a2x squared and so on and so forth. Okay, so let's assume that I want to fit my data looks, it fits the best as an exponential function. So I want to fit this one. Okay, so these are my data points. Okay, and I want to find the error. The error is the difference between the measurement minus the model. Okay, so this is my measurement. This is what I measure, and this is the measure or actual, and this is my model. And here is this is the error. So again, I will take the square of the error. Okay, perfect. So I want to find the summation of the residuals. So this is my measurement. This is my model. Take the square. If you recall, we have two variables. We have a and we have b. So we take the partial derivative of this with respect to a, the partial derivative with SR with respect to b. Okay, so it does just take the partial derivative of this with respect to a, so it becomes 2 times the brackets times the derivative of this with respect to a, so it's basically minus e to bx of I, and then we do the same thing with respect to b, so we get this formula. Now, so we have two equations with two unknowns, a and b, and when I solve of them, so we rewrite them here again. Just this is the same equation. I just rearrange them. I didn't do anything here except rearranging them. So this is the first equation. This is the second equation, which they don't look very friendly, to be honest with you. Okay, so we're trying to solve of them. If we solve the first equation in terms of a, so I will take this to the other side and divide by this. So this is your a. But a here is in terms of B. Okay, A is in terms of B. So we have, remember, this has to be constant. This has to be data, directly data from the X and the Y. Still, I have a variable here. So what I will do here, I will take this value of A and come and substitute it here. Okay, so now I will have one nonlinear equations only in terms of B. We don't have A here. So this is one equation in terms of B. Now, how to solve such equation? Such ugly equation, to be honest with you. I mean, there is no way that I can solve it using linear algebra. So I have to go back and solve it using something using numerical method like the bisection method, like the Newton's method. So I have here like an equation, non-linear equation in terms of B of X, and it will be very, very complicated formula. Okay, and have to use the bisection method or Newton-Raphson. So I have to have an initial guess and may not have. So it's really a mess. That's not really a good way to solve this. So how to solve those nonlinear equations? This is what we'll be learning next week. We will learn a technique to first, we will linearize those nonlinear equations. So we will have a linear equation out of them in different, it depends on the equation I want to fit. We will first linearize this. Once we linearize the problem, then I will have it in this format, y equal to ax plus b. Then I know how to find a and b using the formula, and then I will go back to the non-linear model. Depends on how I went from the non-linear to the linear. I will go back from the linear to the non-linear, but the problem become much, much easier, and that will be the topic of our lecture next week.